Okay, welcome everyone to this continuation of what is quantum topology. Today part 11, and I like to talk about my favorite part about like classical category theory, adjoint functors, or how I call it, the zigzag relation. So in diagrammatic calculus, I usually like to denote adjoint functors like that, and then essentially the relations they satisfy is they are pseudo inverses of one another. Yeah, it's not really an inverse, like a pseudo inverse, and you can kind of straighten out strings. But today, just plain algebra, no straightening out strings, but kind of straightening out strings. So we'll see how it goes. Okay, life is not invertible. Yeah, so you can't undo your mistakes. I have done so many mistakes in my life, and I wish I could undo them, but I can't. So life is not invertible. So invertibility is a little bit of a kind of a weird condition, if you want, right? So life doesn't satisfy that. And here's an example, more mass example. Yeah, the inclusion of the integers into the real numbers is not invertible. There are way more real numbers than there are integers, right? And indeed, the integers are not the real numbers, right? They're not equivalent, not isomorphic. They're really not the real numbers, no matter what you do. There's not really any nice way to assign an integer to a real number such that you can really honestly undo everything. You can undo it on the image, that's not so difficult, but like honestly undo on all of the real numbers. But they're really good approximations, so there's no nice map from the real numbers to the integers. But kind of they're pseudo inverses, like ceiling and floor functions are pseudo inverses to just sending an integer to itself, right? Sending 1 to 1. There's a pseudo inverse to that. Let's say whatever ceiling or something, so where you send something like 1.5 to 1 as well, right? So you just put it, so it's kind of pseudo inverse. So here's ceiling and floor. No, sorry, ceiling and floor, the other way around. So they're kind of pseudo inverses, and maybe life is not invertible, but maybe life is pseudo invertible. So you can work on your mistakes, right? You can still work on your mistakes. You can't undo them from time to time, but you can still work on your mistakes. So in that sense, life is pseudo invertible. And in category theory, it takes the following form. So here's a beautiful picture, which I forgot where I stole it from. But anyway, so you have a functor from C to D, and you have a functor from D to C, F and G. And isomorphism is that they're equal to the identity functors. Very bad in category theory. Never happens. Very, very bad. Equivalence, much better. They're equivalent to the identity. Kind of okay, but let's say it's also kind of rare. Way more often is that they're not equivalent, but they kind of approximate in some sense the identity, and that's usually an adjoint pair. So there's just a map to the identity satisfying some conditions, or there's a map from the identity satisfying some conditions. So essentially, no objects, please. So in category theory, equality is always wrong in category theory, right? Equivalence is better, but it somehow still involves the objects. And kind of the whole idea of an adjunction is to not talk about objects at all anymore. More about like similar type of flavor or morphisms or something like that. So what you really do, or very often, is the following type of construction. The free functor, right, is a pseudo inverse of a forgetful functor. You can go from something like vector spaces. This is supposed to be vector spaces like a C, to set. That's just forget. And there's not really any good inverse, but there's a pseudo inverse which assigns to every set its free k-vector space, the free vector space. And these free, forgetful free pairs, pseudo inverses, adjunctions, whatever you want to call them, they're like everywhere. So our favorite category 1 cop, or my favorite category 1 cop, so not quite 110, let's forget about the crossings, let's just look at 1 cop, is like the pseudo inverse of a functor from symmetric pivotal categories, whatever that is, we'll see what that means, into sets. And it's like the free thing arising in that way. And free is always somehow good. So free free group would be Z, for example, the integers with one object generated by one element. So free is always like without relations, like easy. Yeah? And the free constructions are usually kind of the pseudo inverses to forget. Yeah? Forgetting, you can't undo if you forget something, you can't undo that, but you can kind of work a little bit about yourself, on yourself. You can work a little bit on yourself. And this is like the pseudo inverse is the free functor. And the formal definition of an adjunction is two functors c to d, g to d to c, so f c to d, c to d, and g d to c form an adjoint pair, and this is really a pair in one direction, because kind of the composition here matters. If there's a natural transformation between them, essentially this expression here, this isomorphism where you can swap fxy to xgy, is the same as saying that there is a map to the identity. I hope I do it the right way around now. Could be the opposite. Doesn't matter. There's one thing that really works, and it doesn't really matter which one is which, and the other one to the identity, such that you can play this adjunction type game, right? Adjoint comes from the word adjunction, and in this case, f is a left adjoint because it appears on the left in the home functor. Right here is on the left of g, and g is a right adjoint of f. And a little bit nasty is that the order here matters, so which one is a left adjoint, which one is a right adjoint. But anyway, not all functors do have this pseudo type of inverse. Yeah? So it's an isomorphism on home spaces. You can see it here. It completely ignores the object. It's this pseudo type inverse. And yeah, but they exist there pretty often. And if they exist, they are essentially unique. Yeah? And the slogan is adjoint functors are everywhere. And all what we have seen so far, this one, it's all adjoint functors. There are plenty of adjoint functors. Let me just make this one a little bit clearer. So if you take R as a category where the objects are just the real numbers, and you draw an arrow between them if one of them is smaller than the other, and you just take Z in R as a subcategory, then there's obviously an inclusion as a subcategory, right? It's just you just define it to be sitting in R. Cool. And then you have the adjoint pair, left adjoint of the inclusion and right adjoint of the inclusion, the ceil and floor function. And to prove that is not difficult, you just have to use this type of equation here. Anyway, so eventually this will boil down to this type of equation for the functors. So the left adjoint and the right adjoint have this pseudo-inverse property that you can kind of straighten them out in diagram calculus, but we need a little bit more notation to really set that up. But anyway, the adjoint functors have a very nice diagrammatic presentation, so they will appear in quantum topology because quantum topology is essentially diagrammatic algebra. Anyway, I hope you enjoyed this video, and I also hope to see you next time.